It's a pleasure to be here and be back here. This is the third Master Forum that I've participated in. We've got a good panel. Let's keep this very informal. We're going to have question and answers at the end of this session, but if something burning comes up, go ahead and ask it anyway. We'll figure out how to manage the time. And I'm going to take off my watch, put it right here so I can make sure that we stay on time. The first section is myself and Jody Singer, and we're going to talk about the development of the shuttle, but we're going to go a little bit beyond that. I'm going to step all the way back to Apollo, even pre-Apollo, talk through some of the things we did in Apollo, how that transitioned into the Space Shuttle, but then I'm going to extrapolate from there to Space Station, to Constellation, and then to today. So nobody told us we couldn't do that. So in this panel, we probably have 200 years of experience amongst us. Jody's the youngster, but we have a lot to share with you. We want to share it. There's details in the program that we'll talk about and our lessons learned. They're also, from a top level, the things that we saw in the programs and how they've changed from Apollo to Space Station to Apollo to Shuttle to Space Station, Constellation, and to where we are today. So it's things are ever changing, but they're always challenging, and we want to help you to understand how you can best make a success of NASA and to, as Bob Banner said, succeed. I mean, if anything else that we leave this thing with, succeed in what you're doing, because that's the most critical thing. This, we'll start off with the shuttle, as the title said, an absolutely awesome machine. It was asked the other day, well, what was the behind the shuttle and the formulation of it and the development of it? It was to be the national transportation system. And it was to be the launch system, delivery of goods to orbit for all agencies in the nation. NASA, DOD, CIA, NOAA, everything. It was to be the single launch transportation system. So we worked on that for a long time, and we got to where it was. So I thought what we would do is let that be the basis for our discussion, and then cover with the panel members, talk about the overall program management, the development. Jody's going to speak about the propulsion system development, then Russ, the launch operations. Frank Buzzard's going to, his reflection from an integrated view, looking across the entire spectrum. And then Tommy Holloway is pinch hitting for John O'Neill, who John had a little medical problem, so he couldn't be here. And Tommy Holloway will do that and speak about mission ops. So that covers pretty much the full spectrum. Each one of us is going to speak for 30 minutes, and we'll have question and answers at the end. I want to leave you with the 5 lessons learned that I think came out of the development of the shuttle program. And that is political systems engineering is something that came about in shuttle. And I'll show you how it evolved from these programs to today. It continues to increase. You can see it today. You can see Bob Cabana talking about it, dancing around a little bit about it. But political systems engineering is real. Just my answer to you is deal with it, okay? Know it's there, it's real, and I'll tell you what I mean by political systems engineering. The other thing in shuttle is something that paid well, and that's we froze the configuration. Our schedule had to change, but we didn't change our program plan. So I'm going to talk about each one of these things. Simple interfaces. That's in the execution of the program. How do you make sure you get from where you are today to where you want to be? And the answer to that, when you have limited funds and limited resources and limited time, is you keep everything as simple as possible. And I'll give you some hardware, software experiences of how we did that. Then, as part of management, as part of management, Better's the enemy of good. We make the interfaces simple, but we did not change anything in the shuttle unless it was a make work, and I'll show you exactly what I meant by that. Then the engineers that do the design and development, that's where I spent most of my career, then we rely on the Tommy Holloways and the ops guys to save our butt, because some things don't work all the time, but you get operational flexibility, and that gets you home. So as we talk about this transition from Orbiter to Apollo, I'm going to cover 4 things. Number 1 is that transition, the early formulation of the shuttle, then some of the details, the development of the systems, then early operations. In the transition, absolutely totally different between Apollo and shuttle. The political environment became more and more complex in the shuttle. The bureaucracy and oversight increased. The technology requirements decreased between Apollo and shuttle. But then we had something new came along. We had to keep it sold. With the changes in Apollo were dramatic. Apollo program, you don't have the benefit that we had in Apollo. Pure and simple. In the Apollo program, we had the president that said, go do it. We had the congressional support that said, go do it. We had the public support that said, go do it. So the political thing was very, very simple. Technologically, it was a bear, okay? Shuttle, that program was sold to the White House. We need to do this. We need to someday have this transportation system. So the concept was sold, as opposed to the leader saying, go do it. This was a selling program. So what we had to do is we had to learn how to keep it sold. In the Apollo, the management could focus on the technology challenges. In the shuttle, the management had to do a little bit of both. We had to both focus on the technology, but we also had to focus on the political aspects. Apollo, I guess the simplest way to say it is, we didn't know what we didn't know when that program began. When the president said, go do that mission, go put a man on the moon and bring him back safely to Earth, we hadn't even put anybody in space. John Glenn had not flown. Alan Shepard had gone up and kissed the edge of space. We didn't know how to navigate. We weren't sure how to communicate. We absolutely didn't have the propulsion system. We didn't know if people could live a long duration in space. We didn't know if we could rendezvous in space, but we said we can do it. We did it. There were huge technological changes there, and there are books written on what those things were. Shuttle, a lot simpler technologically. We had 4 major areas that we had to focus on. They had to focus on propulsion system, which Jody will talk about. The thermal protection system was a whole new technology that we had to develop. The avionics was new. How do you control this vehicle coming back 18,000 miles an hour, 10,000 miles downstream, hit a 2-mile runway, at a couple of 100 miles an hour? The avionics, the control systems and all was absolutely breaking the technological barriers. And then something else that was the reusability. We hadn't been there. So those were our 4 challenges, and that was basically it. We had, in the shuttle program, balance those technology in the development with routine operations. Apollo, we didn't have to reuse it. It was fly it, send the guys on their mission, bring it back, and everything was discarded. Shuttle, that was not the objective. So there was a whole new slant on that. But in the shuttle, as I said a while ago, keeping it sold was not an issue with Apollo. Everybody was absolutely behind the thing. In shuttle, in Apollo. In shuttle, we had a continuous challenge. I thought that shuttle would probably be the most frustrating program that would ever exist in NASA. Boy, was I wrong. I mean, we had to, at the beginning of the program, we had to replan the program. Probably a lot of you here don't know that. Every year, the budget that we asked for, we didn't get, so we had to reconfigure the program. The thing that we did is we let the schedule vary. We never changed the content. The other thing that was a real challenge for us, different in Shuttle and Apollo, we didn't have any gee whiz events. We were talking to Bob Cabana about that at breakfast this morning. In Apollo, there were launches all the time. There were failures. There were unmanned missions. There were other things that the public could see, and you could see real progress being made. With Shuttle, you didn't see anything. Shuttle program began in 1970, began the design and development with rigor in 72, but you didn't see anything until the approach and landing tests. That was hard to keep that program alive. As a matter of fact, it was almost canceled several times, but we continued to make progress. Finally, we got down close to in the like 79, 80 time frame. We had some issues. I'll tell you about some of those issues, but we had an associate administrator, John Yardley, and his objective then was, pardon my French, but get the son of a bitch in space. You know, we had to show progress or it was going to be canceled. So we did that replanning every year, and long story short, we got there. And I guess if I look at Apollo and I look at Shuttle and I say, what's changed? You know, we had huge technical problems in Apollo, simple political. In the Shuttle program, we had 4 or 5 technical challenges, but the political environment changed. So I thought, well, we've got something called the conservation of program management complexity. Let me jump forward to today, okay? Let me jump forward to Space Station. Space Station technologically is not very challenging, okay? I mean, it's hard operationally to figure out how to get all those parts up there and make the system work. But there wasn't any technology advanced in Space Station. Politically, it was a bear, okay? We started with one configuration, we ended up with what we have today. It evolved over a lot. We didn't have the Russians on board initially, now we do. So politically, that program has been changing a lot. So today where you are is just try to reflect on this as how it's evolving and see where you are and know that you will make progress and you have to make progress, but you're not going to have the benefits that we had in Apollo. That's just the way of life. In the early formulations of the shuttle program, we looked at a lot of different options and we froze the configuration, and everybody knows what this thing was. It was, you know, we had a set of requirements that said it's going to be the National Transportation System. It's going to deliver 65,000 pounds of payload, 15 feet in diameter, 60 feet long, send it up there, bring it back, reuse the shuttle, design every shuttle for 100 missions, 400 missions total in the life. So now we're ending the program after 40% of the life of the Arbiter, but so be it. That's the political part of the challenge. We had a cross-range requirement that the DoD had. So it's like, let's say, well, let's take something the size of a 737, and that'll, if we open up the fuselage, we can put that payload in it. But by the way, you know, it doesn't have a thermal protection system. It's aluminum, so you have to protect for that. So that's kind of the way the Arbiter evolved. We wanted to keep it simple, but yet rely on things that we could, from our experience. So we looked at a myriad of configurations. We looked at a completely, we said reusable. Okay, by God, we can do that. We can fly back the first stage. We can fly back the second stage, and it'll be completely reusable. Cost a lot of money. Didn't work politically because we couldn't get the funding to do a fully reusable system. So we evolved into something that says, okay, we'll be a partially reusable system. This part's going to be fully reusable. This we can use a few times. This we're going to throw away. So that's what we had. All of a sudden now we're getting into compromise. We looked at that over a period of time, then we balanced that development and operations cost, and we came up with the program that we had. The thing that we did in shuttle that we the NASA, okay, the nation, we had a baseline design in shuttle, and we never changed it. I'm just going to let that sink in. We didn't change anything. We did some, visibly. We had to make work changes in some of the propellant flow systems, in some of the thermal protection system, the way we attached it, and some other things. But visibly, we didn't do anything. And that said a lot for the program. That let us keep going where we were, the mission on which we've objected. The Arbiter original development cost was supposed to be $5 billion. We developed it for that. We delivered the Arbiter per that contract, per that objective, for $5 billion. But we had a mean little manager, Aaron Cohen. Everybody thought he was really nice, but you never worked for him. He was a mean little sucker, let me tell you, because he could say no to so many people that you couldn't believe. He had astronauts, Bob Cabana's gone, isn't he? He had astronauts come into his office every morning at 7 o'clock, and he would meet with anybody anytime, and he would listen to them, but he'd say no. After we started the early design, the reaction control systems were on the fuselage. Not a very good control authority when you're doing that. So guys came in 6 months into the program, 2 years in the program. Let's move the reaction control system out to the ends of the wings, because now, by God, you could, smaller propulsion system, you really have major control authority. The answer was no. We had a little bit of an instability problems. Well, we'll fix that. We'll put canards on the front of the Arbiter. The answer was no. The only thing that we did in that program to change it, we added a heads-up display, and that was it. So the philosophy was, don't change the configuration. You can change the content if you need to, but we're not going to do that. So we had a philosophy, better is the enemy of good. And anytime we deviated from that, it bit us. There was, in the certification program, we started on the Arbiter. We had 2 full-up fuselages, Arbiter airframes. We had a complete fatigue test article, we had a complete static test article, we had a full-up system forward fuselage, thermal vacuum full-up system aft fuselage, and that's the way we start the program. The funding started getting cut, so all of a sudden we had to be innovative what we're going to do. Remember, we said we're not changing the configuration, so what we did is we figured out how to do the design and the development and the certification without compromising safety, but we eliminated all of those test articles. Now, we had to change the way we were flying the vehicle early, but with that, we saved the program. We would have never gotten there had we said, no, we're not going to do it until we get the full program that we want. We're going to have all of our test articles. So we took the airframe, we took the Challenger airframe, to be the Challenger airframe. We tested to 120% of load. We pre-predicted the response of 3,000 strain gauges before we applied the first load to it. Said if we can pre-predict the response of those strain gauges, then we know our math models are correct. And then we can extrapolate to ultimate load, and therefore that should be good. The engineers, we were satisfied with that. But the management and headquarters says, well, we hear you guys, but we don't know. So they brought in an outside group to look at what we were doing, to grade our papers. So they had industry come in that were designing and building the DC-10, in some of the wide bodies, the 747. They rang us through the ringer, okay, on that. We convinced them that we knew what we were doing, and that was a good thing. It worked. But we had to be innovative of how we were doing that. We flew the early test flights thermally so that they were as benign as possible. We got data, we extrapolated, and we said we really didn't need to have the complete thermal vacuum tests as we'd originally planned. So it's it's necessary to think outside the box sometimes in what you're giving up in a program. That was our structural test article. Some of the, when you get into the details of the systems, the development of the things are critical, and the best way to do that is to keep the interfaces and the systems as simple as possible. Give you a few examples. When we started designing the orbiter, Johnson Space Center had that responsibility. Marshall had the responsibility for the payloads. So in 1973, we said, okay, we're ready to design the mid-fuselage to accommodate the payloads. Tell us what the payloads are going to be. Well, we waited and we didn't get an answer. Well, that was a dumb question to ask them, because they had no way of knowing, with all of these users of the shuttle, from DOD to CIA to everybody else, what they were going to be. So what we had to do, what we did is we decoupled the design between the mid-fuselage and the payloads. When you get into something as lightweight as the orbiter, if you put something tied in integrally that participates in distributing the load between the two, and all of a sudden you have to design the two coupled. So we said, we'll decouple that. So we attached the payloads in the orbiter, so it didn't care what was in there. It cared about the mass, but it didn't care what the stiffness of the payload system was. So we decoupled that, and then we ran a myriad, 10 million load cases by a Monte Carlo analysis of a single payload all the way up to 5, of 65,000 pounds payloads going up, CG forward, CG aft, blah, 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 blah. We designed the mid-fuselage that way. The orbiter has never had a problem accommodating, to my knowledge, any of the payloads to be flown. Says, yea, verily, what a good boy are we. You know, we did that. Now we have the crew cabin. The crew cabin is a critical component of the orbiter, and it's a pressure vessel. So we said, instead of making it an integral part of the fuselage, let's make it a pressurized vessel, so that it's nothing more than a thin skin human accommodation thing, just designed by pressure alone, okay? So we said, that's what we'll do, and we'll know the integrity of that. We can check the integrity, and we'll just attach it at hard points in the forward fuselage. So again, kind of like the payload, we separated it from the rest of the airframe. So we made those simple interfaces, and that let us proceed with parallel development. And we reduced the program complexity. The other thing that we did is we'd had a lot of problems in the previous programs, Apollo and so forth, with mechanical systems in space. They didn't work for various reasons. Thermal gradients, hot, cold, galling, the vacuum effect on the materials. So we knew in the payload bay doors that we had to close those doors. We had to open them on orbit to get the payload out. The radiators were there, but we had to close them, because if you can't close the payload doors, you can't come home, because plasma gas would flow through that vehicle, and it would not be a good day. So we knew we had to close them. So what we did is, probably not known to a lot of people, we made those doors extremely flexible. They're attached along the longeron, along the hinge line, and with the flexibility, what we did to assure that we could close them in space, as the payload bay doors closed, if they didn't align properly, the latches started being closed from here around the circumference, forward and aft, so we would zip it closed along the forward and aft end of the payload bays, and then we zipped them closed along the center line. So that's worked on every single mission. We've never had a problem, but we paid for it in the design of the orbiter. Now, instead of having this structure to participate in the bending of the orbiter, it didn't get to do that. You can't count on it. If you're not going to count on it in space, you can't count on it during flight. So we had to make the longeron a little bit heavier, but it's those kind of details and subsystem development that let you do that. That's the crew module, and what I said, it's just a pressure vessel, okay? It carries some mass, but it's attached here. It's attached to the point down here, a point down here, and it's very simple. So it's isolated from the rest of the fuselage. We didn't do as good on the thermal protection system in a simple interface. We spent a lot of time looking at how you protect an aluminum airframe to 350 degrees from a couple of thousand degrees on the surface and 3,000 degrees on the leading edge of the wing, but areas at the bottom are getting up 2,500 degrees. And so we focused on the thermal performance of the tiles in the thermal protection system, and we did a great job. And so we said, well, we're smart enough to know that what we have to do is keep this interface between the tiles and the aluminum structure, that we had to accommodate for the thermal expansion of the aluminum. The tiles don't expand, they're just fused silica, so essentially zero thermal coefficient of expansion. So we put a SIP material in, a strain isolation pad, which was, really an exotic material. Everybody's probably seen Stetson cowboy hats. Well, we use the same material that Stetson cowboy hats are made out of. It's a felt, and it's loosely woven. And so we thought, yeah, hey, we've got a solution there. This aluminum can expand and contract all it wants to, and we made the tiles 6 inches so that they didn't crack if it was over too large a thing. So we said, we got it fixed. But there was one interface that we didn't think about, and that's if this structure was moved underneath the tiles or the tile tried to move away from the structure, there was some stiff spots in the strain isolation pad. And those little stiff spots were stress concentrations on a 5 psi allowable material of 25,000 tiles, 10,000 of which you lose, and you lose the vehicle. So all of a sudden we had to be creative. And the way we did that, we accommodated go back one on that. We made the bottom of the tile stronger, okay? It had to be strengthened twice the allowable that it was. And a young engineer, Glenn Ecord, in the laboratory one weekend, determined how he could double the strength of the tiles without adding any weight. He just stuffed silica powder basically into the tiles, and so that's called tile densification, and that was the answer. Had we found that problem earlier, we'd have gone with a heavier tile, and we would have probably not been able to carry the payload we wanted to. So there were our simple interfaces. That helped us get through the program. Early operations. We had to stay within the capabilities of the program, and we relied on operations to help get us there. We had an early surprise on STS-1. We couldn't simulate it on Earth. You can today in some of the wind tunnels. We found out the center of pressure on the wing was further aft and outboard during ascent, so we had to tailor all the subsequent missions for the next probably 10 missions to make sure that we didn't overload the wing. We stayed within those parameters. The ops guys saved the development guys' butt on it. Another example of better's the enemy of good on STS, I don't remember, Tommy, I think it's probably about STS-3, something about there. We had a fuel cell we had to shut down because we had contamination in the line, in the hydrogen line. We've got the vehicle back and we said, well, shoot, that's easy. We'll put a filter in the line. If there's any debris in the line, that'll fix that. Well, if one filter is good, two's got to be better, right? So we put 2 filters in. Between the 2 filters, we trapped hydrogen gas, put the hydrogen gas into the ullage tank. Well, we could have blown up the vehicle on space. So better is the enemy of good. Just do what's necessary and stick with your philosophy. The other part was, a challenge was planning for spares. That's not a very sexy thing, but it's critical. You can see it in the space station today. Logistics is a big thing. On any program that you're going to be involved in, logistics will be critical. So we learned a lot from Shuttle, and you got to put it in at the very beginning. And I think I got a 5-minute warning there, but I think with our segment we're okay because Jody's going to have that. We'll do the question and answer at the end. Let me just spend a minute on this. And this was critical in Space Station, and I was fortunate enough to be the first program director on Space Station, and I decided that this vehicle, the space station, the facility, had to be designed so it's available to do what it wants to do. Bob Cabana was talking this morning about seeing what the crew is doing. Well, crew maintaining a space station is not letting it be a research facility. And I think probably about 70% of the time now, their time is on research is what it's supposed to be. But to do that, every piece of hardware, every black box on the space station or any Mars program or lunar program, you have to design it with logistics in mind. Is that black box going to be good for the life of the entire program? Is it going to have to be maintained? Who's going to maintain it? Where are the spares going to be? So you have to do a complete systems engineering of everything that's going to fly. We didn't do that in Apollo because it wasn't necessarily. We didn't do it in Shuttle because we were bringing it back. But on a program like a mission to Mars or something, every single element that leaves the Earth has got to be systems engineered to understand what the life is of that thing. So it's complicated. Another part of our success is in the shuttle program, we never changed the senior management from day one to the time it flew, period. We had a little gathering of some of the groups of people there after the STS-1 shortly thereafter, and so that's again is an environmental change. You know, you're seeing management change a lot. Just it's a complication, but it's something that can be dealt with. We had the good fortune not having to do that. Space Station is I had this chart one time and said, to date, this has been the ultimate in changes. It had been, okay? It is the ultimate in changes that we've had to date until Constellation came along. We changed everything. We changed program management, changed baseline configuration, changed the partnership, budget schedules, and logistics. It's a variable program, but it's been successful. So the agency has learned how to deal with these changes. Remember, Apollo didn't change at all. Shuttle changed very little. Space Station changed a lot. Constellation has changed humongously. That was the space station when I was the program director. You can see what it looked like then compared to what it looked like today. You don't see any Russian vehicles up there. You don't see a lot of things that are there completely different. So big changes in Constellation. And I want to leave you with one parting message, and that is political aspects of all programs are important today, but it's important that you make progress and anticipate the changes. You know what you're supposed to do it, keep it as simple as you can to be successful, and let all these other things, let somebody else worry about that. Bob Cabana was saying that today. You know what you need to do, and if it changes, let somebody in Washington or center directors or whatever accommodate that. So with that, I'm going to turn it over to Jody. Jody's going to talk about the propulsion system, and then we'll have a break, and we'll talk about some other aspects of program evolution. Jody Singer is the resume. Thank you.